So, and this is what we call the relative rate test. So the relative rate test is proposed by McCulloch and colleagues. They try to ask if the two lineages diverge from the common ancestor, then they evolve at the similar time. This is the two different lineages. Okay, that's back to the two lineage state. They diverge at the time t. But now we want to ask, so we know these two lineages evolve independently for time of t. Then we want to ask whether the changes on this lineage also accumulate at a similar rate. So given what we know about neutral mutations and the fixation probability, if everything are equal in these two lineages, they should accumulate approximately similar amount of changes, given the time t is the same. So that's the idea. And we want to test whether the observed data are agreed with our thinking. So that's a very simple idea. And this is the diagram from here. So usually you need another species, and this is the ancestor of the A and B. And you want to ask whether A, the OA lineage, is evolved at the same rate as the OB lineage. And this is just a straight line. So the distance between any of the two organisms can be calculated from this topology, right? That's showing in this slide. So we say the differences between A and B, the genetic distance between A and B, are the distance for this lineage and this lineage. So this lineage is the OA, this lineage is the OB. So you can use a different notation, so you can write KOA or KOB is the same. And the distance just added the two together. So that's a very simple idea. And if these three can be calculated, can be estimated, so the distance, so what you can calculate is KAB, KAC, and KBC, right? Because you have three sequences, you can calculate the distance using the sequence information. So that can be direct, that's what the books say, you can direct estimate from your sequence information. And what we would like to do is to use these three numbers. There are three different distances. Use three numbers to calculate the distance in this lineage, and the other lineage. And given the divergence time is the same, we want to ask whether these two lineages are evolved at the same rate. So ideally, I already told you, the null hypothesis is these two are the same. So the differences between the two should be zero. That's the null hypothesis. Then the whole idea is to ask whether our estimate from the sequences is significantly different from zero or not. So that's the test hypothesis. So it's either is zero or not. And we use the statistics to say it's significantly different from zero or not. If they have no differences, then we say they agree with null hypothesis. These two lineages evolve at a similar rate. If the statistics tell you it's significantly different from zero, then you say the two lineages will evolve at different rate in this locus. So this is the thing we do. Okay, so this is the results from an example from your study. We test the mouse and rat difference. So in this two lineage, And the same thing, we calculate. So 1, 2, 3 is equivalent to the A, B, and C in the previous slide. So we want to know the calculation from the sequence is in the first 3 columns here. So the K12, K13, and K23. So those are the sequence comparison. We can calculate the rate of differences, right? So that's the formula we learned from chapter 3. Then in the test of the substitution rate, we do want to compare the K13 minus K23. That's from the slide. So we know from the previous slide, so in your book you have to put them together. So if we put these two together, we compare these two and use K13 minus K23, and actually we are compare the lineage from O to A and O to B, because O to C are shared by the distance, right? So we are comparing these two lineage. And that's why we compare the distance between lineage 1 to lineage 3 and lineage 2 to lineage 3. Okay. Then you do statistics. And the bottom line here is the two number, although they are not 0, but the two number does not show significant differences from the neutral hypothesis is 0. So the conclusion is for the rat lineage and the mouse lineage, they evolve at similar rate in the past. So this is what we do with all analysis. And this is a very simple analysis, the rate of test of the evolution rate, equal rate test. Another way to do that is also similar. It's Tajima's 1D test, is 1 degree of freedom. And this test also consider, although the notation here looks not so friendly, but you don't have to worry that too much. This is just like from your textbook. But still the same thing, we consider 3 lineages. But we consider 3 lineages with different change differences. So we have all kind of differences, but I want to show you the next slide. As he wants to compare only 2 types of sequence differences, M1 and M2. So M1 is what we call I, J, J. The third one is the R group. And the I and J means the sequence you want to compare, the 1 and 2 lineage are different at this position. And the only possibility are listed like next to the second equal sign. Okay, so this is like A, G, G, A, C, C, O, this. That's M1. So M1 means the mutation happened at the lineage 1, right? Can you see that? So if you write, okay, let's write the first one. It's A, G, and G. M1 means the change happened at the position 1. Which one is better? So this is the M. So M1 is the one using C, the third sequence as the L group, and the changes happen in the lineage 1. That's M1. So I say, oh, the notation looks, the previous slide looks not so friendly, and this slide you haven't really tried. If this is the first time you observe that, you still try to look at what the relationship between the M1 and M2. So M1 is the change happen in the lineage 1. Similarly, M2 is the mutation happen on the lineage 2. And so the same idea, he asked, Tajima derived the method to ask whether mutations happen in these 2 lineages are the same. So that's the 2 group, so M1 and M2. That's the mutation or changes occur in these two lineages. Then the expectation, the null hypothesis is like the expected number for these two. So the large E is the expected number for these two are the same. So this one is exactly the same equation for the very beginning of the section, so the 2 slides before. It's just the first equation with ij there is try to show you the possible configurations. But here we only, when we want to do the test, we only consider these 2 types of changes, M1 type or M2 type. And given the same divergence time, you have heard me say many times in this hour, the expectation should be the same. So the expected number for these two is the same if they evolve at the same rate. So that's the expectation. And you can do test, chi-square test, to ask if the 2 numbers are the same or not. So that's a very simple 1 degree of freedom Tajima-D test. So this is the Tajima, I should say Tajima 1D test, because we'll learn another Tajima-D test after the spring break. So in this way, it's a very similar but different test, but test the same null hypothesis. And this is a diagram we can observe here. So this is a study to look at all the African apes. I like to say all the African apes, but I'm inspired by the book named The Third Chimpanzee, which is us. We only know there are 2 chimpanzee species. So the Third Chimpanzee, the book, is talking about what our status in the hominoid compared to all the living African apes. So if you haven't seen the book, I really highly recommend it, because we'll talk a little bit about that today. So in this table, we count all the numbers. So actually, it's not a very difficult calculation. And just count the numbers on each lineage and ask whether the numbers are the same or not. So that's the M1 and M2. And in here, just look at all the comparisons. And immediately you can spot the statistical differences. I already boxed it on this slide. So the lineages to the humans are the one evolved very differently from all the rest. And actually it evolved slower in this lineage.